In this video we look at the work on circular motion in a vertical circle for Unit 3 of the WJEC Further Mathematics specification. We need to be able to understand and use the mechanics of motion in a vertical circle. So for the general motion in a circle of radius r, the speed v is linked to the angular velocity theta dot by v equals r theta dot. There's an acceleration towards the centre of the circle of magnitude r theta dot squared, which is equivalent to v squared over r. And there's also a tangential acceleration of magnitude r theta double dot, or v dot, in the examples that we're going to consider. The circle will be vertical, the conservation of energy will usually be applicable, and Newton's second law will be applied radially. For some harder questions, it may be necessary to apply Newton's second law tangentially, but this is excluded on the WJEC FM3 specification. So, our strategy for vertical circle questions will be a nice clear force diagram, which should show the radial acceleration. We may well need to do some geometry or some trigonometry. We should apply the conservation of energy, and then we should apply Newton's second law radially. We shall have a look at this process with two examples. So the first example, we have a diagram showing a particle P of mass 3 kilograms attached by a light inextensible string of length 0.4 meters to a fixed point O. Initially, P is projected from the point A, which is vertically below O, with a speed of 4 meters per second. And in the course of the question, the first two parts we've got to consider is we've got to show that v squared is equal to 8.16 plus 7.84 cos theta, where v is the speed when OP makes an angle theta with OA. And we also need to find the tension in the string when P is in that position. So, our first task should be to draw the force diagram and make sure we've got our radial acceleration shown in on the force diagram as well. So for the forces, we've got the weight of the particle P, which is 3g, and we've got the tension in the string, which we'll call T. We've then got the radial acceleration, and in this question, because we're dealing with the speed of the motion, we shall use the radial acceleration in the format v squared over r. And onto this diagram, we'll just also add the initial speed of 4 meters per second at A, and the speed of v meters per second when the particle is at the point where OP makes the angle theta. So we've got v meters per second there. Before we can apply the conservation of energy, we're going to need to calculate the height gain that the particle has made in moving from its initial position to this general position. So, if we look at the diagram we've just presented. The height gain we want is this value h that we've got here on the diagram. It should be clear that h is 0.4 minus x, but that x is 0.4, that's the radius, times by cos theta. So we've got h is 0.4 minus 0.4 cos theta, or in other words, h is 0.4 times 1 minus cos theta. We can now apply the conservation of energy. So at A, the particle has just kinetic energy, if we are using the level of A as being a zero potential energy level. Whereas at P, the particle has got, or in the general position rather, the particle has got both kinetic energy and potential energy. So our conservation of energy, which of course assumes that there's no air resistance present, says that the kinetic energy at A is equal to the kinetic energy at P plus the potential energy at P. Kinetic energy at A is going to be a half times the mass, 3, times the speed squared, which is 4 squared. So we've got a half times 3 times 4 squared, equals the kinetic energy at P, which is going to be a half mv squared. So that's a half times 3 times v squared, plus the potential energy at P, which is going to be mgh. So that is 3 times g times by h, which we know is 0.4 times 1 minus cos theta. So if we simplify these terms, we've got 24 equals 1.5 v squared plus 11.76 minus 11.76 cos theta. In other words, 12.24 equals 11.76 cos theta. So 12.24 plus 11.76 cos theta equals 1.5 v squared. Divide through by 1.5, we obtain v squared equals 8.16 plus 7.84 cos theta, which is the expression we were being asked to show in part A. Moving on to part B, we're going to have to find the expression for the tension in the string when the particle is at this general position. Using Newton's second law towards the centre of the circle, we've got T minus the component of the weight, and the component of the weight is going to be 3g cos theta. So we've got T minus 3g cos theta must equal the mass times the acceleration, so that is 3 times by v squared over r. So we've got T minus 29.4 cos theta equals 3 times by v squared, which we know is 8.16 plus 7.84 cos theta, all divided by the radius, which is 0.4. Need to do a little bit of tidying up of that expression. So we've got T minus 29.4 cos theta is 61.2 plus 58.8 cos theta. And which then gives T equals 61.2 plus 88.2 cos theta. Okay, so we've now got to move on to part C, which is to determine whether or not P describes complete circles. So we've got our two expressions for v squared and for t. For a particle on the end of a string to complete circles, we need to be sure that the motion never stops and the string never goes slack. Now, looking first of all at the v squared expression, we've got v squared is 8.16 plus 7.84 cos theta. We know that the smallest possible value for cos theta is -1. So the smallest possible value for v squared is going to be 8.16, take away 7.84. So we've got v squared is always at least 0.32, which means that v can never be equal to 0. So the particle never stops whilst it is on the circle on its circular path. But we must also check that the string never goes slack. Now, looking at the expression for t, we've got t is 61.2 plus 88.2 cos theta. So t will equal 0 when cos theta is -61.2 divided by 88.2. In other words, when theta is about 133.9 degrees. Now at that point when the string goes slack, the motion will then continue under the effect of the weight of the object alone. In other words, the motion will now be projectile motion. So, in this case, it will not be complete circular motion. The circular motion ceases when theta equals 133.9 degrees and the motion becomes projectile motion. Now for part D, all that has changed is that we have changed the string into being a light, rigid rod. So the two expressions that we've got for v squared and for t still exist. However, with a rod, it is perfectly possible that the tension becomes 0, or indeed it can become negative, in which case the rod is exerting a thrust onto the particle. So all we have to worry about in the case of part D is whether V ever becomes 0. And we've already shown that for this motion, V squared is always at least 0.32. So therefore V is never 0, and if V is never 0, we are going to get complete circles if the string is replaced by a light, rigid rod. For our second example, we have a diagram shows a particle of mass 3 kilograms at a point P on a smooth outer surface of a fixed sphere with centre O and radius 4 meters. The line segment S to T is a horizontal diameter of the sphere, and the points O, A, P and S and T are all in the same vertical plane. Initially the particle is held at rest at the point A, where OA makes angle alpha, with OS, where sine alpha is 0.8. Particles then projected with velocity 5 meters per second in a direction which is perpendicular to OA, so that particle moves along the arc joining A to T. So it's going over the top of the sphere. When the particle is at P, OP makes an angle theta with OS. So we've got to find in terms of theta the speed of the particle at P. We've got to determine in terms of theta the reaction between the particle and the sphere at P. And we've got to describe the subsequent motion of P. So again, we're going to start by drawing some diagrams. So there is our starting diagram. We've got the particle now at its general position. We know that when it was A, it had a speed of 5 meters per second. When it's at its general position, we have got a speed of v meters per second. And we're going to draw a force diagram for the situation as well. So the forces acting on the particle when it's in its general position are its weight, 3g, and we've got the reaction between the particle and the surface of the sphere, which we will call big R. Now, we also will put on the acceleration towards the centre of the circle. And the acceleration towards the centre of the circle, because we are dealing with the speed of the motion, we'll write the acceleration towards the centre of the circle as being v squared over r. So, what we want to try and do is we want to try and find an expression for the speed of the particle at P, and what we will do is we will use conservation of energy again. So again, we're assuming there's no air resistance to worry about. If we're going to use the conservation of energy, it's a good idea to have a clear idea of where we're having our level of zero potential energy. I'm going to use that diameter, ST, as my level of zero potential energy. So, whilst the particle is at A, it's got some potential energy and it's got some kinetic energy. While the particle is at P, it's going to have rather more potential energy and rather less kinetic energy than it had at A. So, we have the potential energy at A plus the kinetic energy at A must equal the potential energy at P plus the kinetic energy at P. Now the potential energy at A is 3 times g times the height of A above ST. And just considering the triangle formed by O, A and the vertical line from A down to ST, we can see that that height there is 4 sine alpha. So the potential energy at A is 3 times g times 4 sine alpha. The kinetic energy at A is a half times 3 times v squared times 5 squared. The potential energy at P is 3 times g times the height of P above the diameter ST, and that height is 4 sine theta. So the potential energy at P is 3 times g times 4 sine theta, and the KE at P is going to be a half times 3 times v squared. So there's my conservation of energy equation. We know that sine alpha is 0.8, so we can tidy the left hand side up considerably. So we have 94.08 plus 37.5 equals 117.6 sine theta plus 1.5 v squared, or v squared equals 87.72 minus 78.4 sine theta. Now, our next aim is to find the reaction between the particle and the sphere when the particle is at P. If we're going to be able to do that, we're going to need to be able to find the component of the weight which is acting radially. So it'd be worth just drawing a separate diagram just to be clear about what this component is going to be. So, there's my diagram. So in the black I have got the triangle formed by O, the centre of the sphere. The line OP is my hypotenuse, and I've got the horizontal coming out from O and the vertical coming down from P. I've got in red my weight of 3g, and I am trying to work out the component of that weight acting towards the centre of the circle, so the radial component of the weight. Now, if we put a few angles on, we've got a right angle there, so therefore the angle at the top of the triangle must be 90 minus theta. As we're splitting the weight into a component which is acting radially and a component which is acting at right angles to the radius, we have a right angle between the two components, which means that the third angle in that little red triangle must be theta again, which means that the component of the weight which is acting radially must be 3g sine theta. Okay, so now applying Newton's second law radially, we've got the component of the weight acting towards O is 3g sine theta minus the reaction, because that's acting away from the centre, must equal the mass times the acceleration, which is m times v squared over r. So we've got 3g sine theta minus mv squared over r is equal to the reaction force. So the reaction force is 29.4 sine theta. Take away 3 lots of v squared. We know that v squared is 87.72 minus 78.4 sine theta divided by the radius, which we know is 4. And that will simplify itself through to the reaction force being 88.2 sine theta minus 65.79. Finally, we've got to consider the motion, the subsequent motion of the particle. So whilst the particle is in contact with the sphere, we know that v squared is 87.72 minus 78.4 sine theta. Now that is always going to be at least 87.72 take away 78.4, because we know that sine theta can be no bigger than 1. So we know that v squared is always at least 9.32 for all values of theta, which means that v is never equal to 0. And if v is never equal to 0, it means that the particle doesn't come to rest while it's in contact with the sphere. However, there's a second thing we've got to be worried about, and that is whether the reaction ever becomes zero. Because if the reaction becomes zero, the particle will lose contact with the sphere and will then start moving as a projectile. So, we need to consider whether r equals 0 or not. We've got r equals 88.2 sine theta minus 65.79. which means that if r equals 0 when sine theta is 65.79 divided by 88.2, which happens when theta is either 48.2 degrees or 131.8 degrees. However, the motion only starts when sine theta is 0.8, in other words when theta equals 51.1 degrees. So we shall ignore the 48.2 degree solution and say that we have the reaction equals 0 when theta equals 131.8 degrees. That means that the particle leaves the surface of the sphere when theta equals 131.8 degrees, and the motion is then that of a projectile.